Hey, all, this is going to be a quick review of factoring. Factoring is actually a topic from Intermediate Algebra, Math 93. So in terms of like testing or quizzes, this section wouldn't be on there explicitly just as a factoring problem, at least if you're taking this course with me. Someone else may use the course page in the future and they may have a different idea on that. But I wanted to do a review of it because so many people struggle with either not having learned this content very well or not remembering the content very well, heading into these chapters where we end up using it as a technique within lots of problems. So with that, let's go ahead and get going. What makes factoring hard is we're going to have like 5 different versions of factoring, and which one you use depends on what equation you're presented with. The first step for any factoring problem is to look and see if it has a greatest common factor, and then to get that out of your way in the event that it does. So these first couple questions are just reviewing greatest common factor. Oops, let me get my pen going here. Okay, let's go scoot that over just a hair. So this first one, looking at 27y squared and 45y, for greatest common factor, we're looking for the largest monomial that divides into both of these. So in terms of the numbers, 27 and 45, the largest thing that divides into both of those would be 9, and y squared and y, they both contain at least a y, so that would be my greatest common factor. In terms of the variables. For variables, you're always looking for the smallest power, and so this is y to the first and y to the second. So I could take 1y out of 1y, but I wouldn't be able to take 2y's out of 1y. So here, if I go 9 goes into 27, that would leave behind a 3 and a y. 9 goes into 45, that would leave behind a 5, and then I already have the y there. So greatest common factors are a lot like a reverse distribute. What you get is kind of what you're used to seeing where you would distribute, and that's actually how you would check and make sure you did everything right. So if I did 9y times 3y, that gets me back to that 27y squared, and 9y times 5, that gets me back to the 45y. This one, same thing. So looks like we have 8, 28, and 20. 28 jumps out at me because it's 4 times 7. So these are not divisible by 7, so 4 is going to be the best I can do. Also notice this is x squared x. This one doesn't have an x, so I can't factor out an x on this. This every term had a y. For this one, every term does not have an x. So 4 is as best as I can do. So take a 4 out front, and it's going to leave us at 2x squared, plus 4 times 28 would be 7x, and then 4 times 20 would be minus 5. Factoring by grouping. So this is a technique that we use when what we're trying to factor has 4 terms. So anytime we see a 4-term problem, and by that I mean 1, 2, 3, 4 terms, it's got to be a grouping problem. It's the only technique that we have at this time. So step 0 is always factor out the GCF if there is one. Step 2, we take the greatest common factor out of the first 2 terms and the second 2 terms. That's the grouping piece of this. So we'll look at the first 2 terms together and the second 2 terms together. And we're going to get something that ends up looking like that, where we end up with this common factor left in the parentheses, and then that common factor gets pulled out front. So much like the GCF that we just did. So let's take a look here. We have xy plus 5y, so what's in common is the y's. So we'll pull a y out front, and it leaves an x plus 5. And then I need this to come up to x plus 5 again. So looking at the negative 6x minus 30, it makes me want to pull out a negative 6, because I need this to be a positive x and a positive 5. If you distribute back negative 6x, negative 30, that's exactly what this was. But it can help to think about what you have right here. Honestly, let me rewrite it for a second. Once I'm to here, I will often just write down x plus 5 again, because I know that's what's coming up, because it's a 4-term grouping problem. And then I look and I see, what do I need to pull out of these 2 to make that true? So in this case, negative 6, for those same reasons. These have to match, because that's going to be your greatest common factor that you pull out front. So x plus 5, and it leaves behind the y minus 6. Every 4-term problem does not factor by grouping, but this is just for the ones that do. This is the technique for factoring those. For that one, let's see. For those first 2 terms, we would have an x squared in common. So we'll do x squared, x minus 8. And again, just kind of distribute back in your head and make sure that everything's good there. And then, like I said, we're going to need to get another x minus 8. So I would have to take out a 5 to make that happen. 5 times x is 5x, 5 times negative 8 is negative 40. Now I have those matching terms there, which was kind of the plan. And leaves behind x squared and plus 5. So anything with 4 terms, that's the plan. And then we head into a bunch of the 3-term versions. So this first one is the easiest. This is when the leading coefficient is a 1. So the number in front of the x squared is a 1, or like the one over here, when we get the greatest common factor out of the way, it's going to reduce down to 1 with a 1. The way that we do these is we ask what multiplies to be the number on the end and adds to be the number in the middle. You might remember this one. This is probably the most common factoring that you end up running into is this. So for 30, let's think through our numbers. What multiplies to be 30 would be 1 and 30, 2 and 15, 3 and 10, and 4 doesn't work, 5 and 6. So that's all my multiples of 30, and I'm looking for the 2 that add to be 13. So 3 times 10 multiplies to be 30, 3 plus 10 adds to be 13. So that is my factors. The reason that we're asking those questions, multiplies to the end, adds to the middle, is if you think about if you foiled this back, y times y is y squared, y times 10 plus, 10, y, 3 times y plus 3y, and 3 times 10 makes 30. So when you FOIL, which is the reverse of factoring, is FOIL is multiplying, factoring is breaking something up into its factors. But when you FOIL, you end up, the ends multiply to be the number on the end, and then they add to be the number, the cross term in the middle. So there's our plus 10 plus 3 that makes our plus 13. So that's how come you want to say what multiplies to be the number on the end adds to be the numbers in the middle. For this next one, this is a good example of this looks much harder than that, and it's because there's a greatest common factor in the way. So let's factor, everything has a 4 in it, and everything has a w in it. So let's go 4w out front. W squared minus 4 goes into 32 8 times, and 4 goes into 48 12 times. And then we just bring down the 4w. We'll set up our parentheses. And then we ask what multiplies to be positive 12 but adds to be negative 8. So 12 would be 1 and 12, 2 and 6, and 3 and 4. So it sounds like 2 and 6 are the ones that are going to work. And then they would both have to be negative to multiply to be a positive 12 and add to be a negative 8. Sometimes we'll ask, does it matter what order you put the 2 and the 6 in? Like, could I have put the 6 first? Yeah, absolutely. It does not matter at all which order you write those in. Okay, this is probably the most difficult of the factoring methods. So this is where a does not equal 1 and also isn't a perfect square, because we'll see a special case in the next part here for when a is in 1 but it happens to be a perfect square. So for this, what we do is again factor out the GCF if it's present, and then we find the product of a times c. So a is your coefficient of your x squared term, c is the constant term on the end. So for this one, 3 times 2 would be 6. And then we look for what numbers multiply to be 6 but add to be negative 7. So it sounds like -1 and -6. So very much like what we just did for the trinomials, where it did start with a 1. But in this case, we have to account for that 3 out front. So we're going 3 times 2 to get 6 to get that number, and then we ask the same the question multiplies to the AC, adds to be the middle. And then what we do is treat it like a 4-term problem. So for this one, I'm going to write 3x squared. It doesn't matter which of these I write first. I'm going to write the minus 6x first, but you could do it either way. So all I've done is taken those two numbers, and instead of having minus 7x, I wrote it as minus 6x minus 1x. So it still makes minus 7x, but I've rewritten it as a 4-term problem. And then we'll use the grouping technique that we learned, or hopefully reviewed, a couple of problems ago. And so I'll look at these first two terms. I can take out a 3x from both of those. So that's going to leave an x minus 2. I need to get another x minus 2. And this is where I like writing that out so I can see where I'm getting to. I need to take a -1 out of that to make those signs work. So -1 times x is -x, -1 times -2 is +2. So it's kind of a combination of the 3-term one and the 4-term one, where we find the numbers that multiply to be a times c, and then add to be the middle, and then rewrite it as 4 terms. And then from there it works just like a grouping problem. So x minus 2 and 3x minus 1. Same thing over here with a little bit harder number. 3 times 20, so that would make 60. So I need two numbers that multiply to be 60 and add to be 19. A few more choices with 60, so if you can't spot what you should use, just start making the list of numbers. So 1 times 60, 2 times 30, 3 goes in 20 times, 4 goes in 15 times, and that's going to be our number, but 5 goes in 12, and 6 goes in 10. And so if you make that list with all the possible factors, you will run into the right thing here, even when it's a hard spot. So here we'll rewrite this as 4 terms, 3y squared. Again, doesn't matter what order I write this in, so I'll go 4y plus 15y plus 20. The reason I picked the order over here was I wanted to show how to factor out that -1, in case you wondered why I wrote it opposite the direction I did the first time. Let's see, out of those two I could factor a y, and that would be 3y plus 4. And from these two I can factor out a 5, leaving me another 3y plus 4. And then this will be 3y plus 4 and y plus 5. And then lastly we have factoring with special products. So special products are these formulas that if something happens to take the form a squared minus 2ab plus b squared, or the same thing with a plus, those ones factor to this a minus b quantity squared or a plus b quantity squared. A polynomial can certainly lead with a square without being one of these special products, but as we're encountering them in these kind of lower level math classes, when you see something with squares on the ends, it probably is of this form. So what I generally do is assume it's going to work, factor it, and then I check myself and make sure that it really was what I was assuming. We wouldn't want to go 49 times 9 and get some giant number and then figure out what multiplied to be that and add to be 42. That would be a much harder problem. So I would, if I see the squares on the ends like that, I would, like I said, assume it's going to be one of these formula ones, and that it has a nice answer, which is a perfect trinomial square. And I'll show you how to check it in a second to make sure it really is what you think it is. So with this, the way it works is that leading term is a squared, the trailing term is b squared, and it's going to factor to a either minus b or plus b dependent on the sign. So if 49x squared is a squared, then that's going to make, is that not working? there we go. Whoa. Okay, there we go. I think we're worked out. So if 49x squared is a squared, then a is going to be 7x, because 7x times 7x would get me back to 49x squared. Since that's a minus, this is a minus. And then 9 is a square, so b squared is 9. That would make b 3, and quantity squared. To check this, this middle should be 2 times a times b. So if I go 2 times, this is a, times b, it should make the middle. 2 times 7 is 14, times 3 is 42. So that means that what I was assuming this was, which was a perfect trinomial square, it really is with that middle term. Again, it's possible to have squares on the ends and have it not be one of these, but largely if we bump into one with the squares on the ends, it's going to behave well and be this. So for this one, again, 25 and 36 kind of yell at me as squares on the ends. I bet it's going to factor this way. So 5x and then plus 6 quantity squared, because 5x times 5x is 25. Oh, it should be a z there. My bad. We'll just rewrite that, make it a z. 5z times 5z would be 25z squared. 6 times 6 is 36. If you were to FOIL this out, let me go ahead and just write this up here. Get rid of that, give myself a little room. 5z plus 6, 5z plus 6. 5z times 5z would be the 25z squared. 5z times 6, so that would be, whoops, I'm jumping, 30z. And then on the inside we get another 30z. And on the end we get 36. And then those two add to be the 60 there in the middle. So that's why you have to go 2 times a times b, is because you end up with two factors that are a times b. So if you spot them for what they are, they're actually really easy problems to factor. They're really hard problems if you don't and you try to do AC method on them. So what you're looking for kind of as the tip-off is these perfect squares. Just made a list of those to make them easy to spot. So if you do see those numbers on the ends of a trinomial, probably going to be one of these. And then our last technique is, this one pops up all over the place, it's called a difference of squares. And so for a difference of squares, if I have something in the form a squared minus b squared, it's going to be a plus b, a minus b. So this kind of came out a minus b, a minus b. There's a pair of them. This one comes out a plus b, again with a pair with the same signs. This one comes out opposite signs. So if I have something like that, it's as easy as z plus 9 and z minus 9. And that's it for factoring those. You can see if I FOILed, I'd have z squared, and on the outside I'd have a minus 9z, on the inside I get a plus 9z, and those terms cancel, and that's why there isn't a middle term. And then on the end we get the 81. So this, again, with the perfect squares, so 2x plus 7 and 2x minus 7. So again, well, if it's me that you're taking the class with, I wouldn't put these on a quiz or an exam. I would just treat this as a review section. That said, this math will pop up all over this next chapter in particular and in other places in the course. So good to have a review of this so that you're not fighting the factoring while learning the new math.